In this section, we're going to talk about stars, all the different kinds of stars that there are, and how in the world have astronomers through the years been able to determine all of the wonderful pieces of information that we have on those stars. So over the last 200 years or so, astronomers have been able to determine lots of things about stars. A lot of variety. There are as many different kinds of stars as there are different kinds of animals. There are vast differences between one star and another. Their temperatures. Some are very hot, some are very cold. The masses, the luminosity, how bright are they? And the distance. How far are some of these stars from us? So we're going to spend this section, this chapter, going through how was all of this discovered and determined. And we're going to begin with a little bit of review, things that we know from the past. First off, as you may remember, a star's temperature is related to its color. If you have any sort of a hot object, it's going to be a black body radiator, meaning that it is going to emit a full spectrum, the full Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, plus some light in the ultraviolet and some light in the infrared and far infrared. This whole entire shape is called its black body curve, and the peak of the curve is going to help us determine, or that peak of that curve will be right around the color that we see that is most dominant for that star. So a blue star will have a black body curve around there, white star a little bit further into the middle of the visible spectrum, and a cold red star is going to have a peak more on the red end of the spectrum. Other things to remember, one is that red stars are the cool ones. Medium stars like our sun are kind of medium in temperature and white, and the hot blue ones, those are those young hot stars like the stars in the Seven Sisters, which are the Pleiades. Another thing to recall or remember are Fraunhofer lines. Now, Fraunhofer lines are these absorption spectral lines that we see due to the chemical composition of a star. A star itself is going to give us the continuous spectrum, the whole Roy G. Biv, all the colors in the visible spectrum. But because the star has a hot gaseous outer atmosphere, as the light travels through that hot gaseous atmosphere, some wavelengths of light are going to be absorbed by those gases, and that gives us huge clues as to the chemical composition of what's within those stars. Well, we're going to begin our story of discovering things about different types of stars by going into a discussion of the Harvard University computers. Now, until about 60, 70 years ago, if you used the term computer, you were talking about a person, not a machine, but actually a person. And in the early 1800s and 1900s, Harvard University had a group of women that they referred to as computers. They had a lot of astronomers that were on staff, but they needed people to actually analyze the data. This was very tedious, painstaking work, very, very detailed, and they needed people who were smart, who knew about science, and it was considered in the late 1800s, early 1900s, unladylike for a woman to be an astronomer up half the night looking out through a telescope. And so the male astronomers at that point in history were out looking through their telescopes, and they would gather data, and then these women would actually analyze that data. If you have seen the modern movie Hidden Figures, the movie Hidden Figures was about a group of women who happened to be computers for NASA, and that was in the 1950s and 60s. Well, this is a group of ladies who are doing the same job, just happened to be a couple generations earlier. So these are some actual pictures of these computers at Harvard, and a couple of them created and discovered some of the most important things in all of astronomy. So the first one we're going to talk about is anti-jump cannon. And here's a picture of anti-jump cannon. One of the things that she took command of in this data collection at Harvard was she looked at the spectra of hundreds of individual stars. And what she did is she organized them by the strength of the hydrogen lines in their spectra. The most abundant element in any star is hydrogen. And she found that some stars had hydrogen lines that were very, very pronounced, very sharp, very strong. And some stars had hydrogen lines that were a little bit weaker, while some stars had hydrogen lines that were weaker or dimmer still. She knew they were from the same element because the spectral lines were at exactly the same wavelength in exactly the same spot in the spectra. They just varied in intensity. So she arranged them by strongest to weakest, and then she rearranged this data by star color. So she took the hot blue stars, and then she took the cold red stars, and she organized all of this data together. And here's what she found. She found there was a relationship between the temperature of a star, and temperature, of course, is related to color, and the spectra. Hot blue stars had a very, very distinctive spectra. Cold red stars had a very distinctive spectra. So what did this mean? Amongst other things, it meant that the cold red stars had a different chemistry than those hot blue stars. The hot blue stars had a very different chemical composition. Now, later in history, this would help us understand the life cycle of stars. How does one star change from birth through death? This spectral classification is very important when you look at a star out in the heavens. The stars fell into order from the hottest to the coolest from O, B, A, F, G, K, and M when anti-jump cannon arranged them by temperature and spectra. And a little mnemonic device, memory device, that she actually invented to keep this straight is O, be a fine girl or guy, kiss me. So O, be a fine guy, kiss me is the little device to help keep track of the order of these stars. And you need to know this. This is definitely fair game on any sort of a quiz or test, that I might ask you something like, I have an A star and a K star. Which one is hotter? Well, this is a hotter star, the A stars, and the K stars down here are cooler. This is a wonderful chart, and it shows the colors of the charts of the stars and their spectral type, oh, be a fine girl, kiss me, and the average temperature of the photosphere, the outside layer of these individual stars. So O-type blue stars have 28,000 to 50,000 degrees Kelvin, incredibly hot stars, and their spectrum is dominated by helium. They are fusing hydrogen into helium so fast that helium is the dominant element. B stars, 10,000 to 2,800, helium and hydrogen, not fusing hydrogen as quickly. A stars, cooler, contain some hydrogen and some ionized metals. Now, when they say ionized metals, basically it's anything larger than helium on the periodic table. F's, 6,000 to 7,500 external photospheric temperature. G's, 5,000 to 6,000. K's, cooler, 3,500 to 5,000. And M's, 2,500 to 3,500. If you know the color of a star, it's not much more to knowing the classification of a star, which will tell you its temperature and what it's actually made of, which is pretty amazing. Because these are large groups, A, O, B, A, F, G, K, and M, there are subdivisions, and subdivisions determining how far towards the O and how far towards the B. And these subdivisions are given numbers, 0 for the hottest, 9 for the coolest. So an A star might come in an A0, A1, A2, A3, etc. For example, here is our good friend Orion. And let's look at a few stars that are here. First off, Betelgeuse is an M2. Now, if you didn't know which star here was Betelgeuse, you would be able to say M2, let's see, M is a red star. Ah, that must be Betelgeuse, and it is. Rigel is a B8, and Rigel is this large, big, beautiful, bright blue star in the lower foot of Orion. Mintaka is a B1. B1 is the right-hand end of Orion's belt. That is Mintaka. Now, our own sun is a G2. That is the star that we call home. So you need to know this because there's no place like home. How do you remember that spectral classification? A 0 through a 9. Which one's hottest? Which one's coolest? Well, hopefully this is going to help a little bit. It's kind of like winning prize ribbons at the county fair. 0 is the hottest. That's kind of the grand prize. It's a big deal and fabulous if you are a 0 star. But then they get cooler, kind of like the ribbons are not quite as, you're not as close to the top if you are first, second, third, fourth, and this goes down to 9. And so that is that subclassifications of stars. On a quiz, on a test, I might do this. I might say, I have an F2 and an F4 star. Which one is hotter? Which one is hotter? Well, that would be the F2, because 2 is a hotter classification of stars than an F4. What if I did this? If I said I have a K1 star and I have a G3 star, which one is hotter? Well, then you might have to go back and go, oh, be a fine girl, kiss me, and say, G's are hotter than K's, so this is going to be a hotter star than that one. So those are some of the questions that you might get asked. Annie Jump Cannon created the stellar classification over 100 years ago. But in modern times, we have modern telescopes that allow us to see into the infrared part of the spectrum, so we can actually see cooler stars. Since that time, 2 new lower temperature classifications have been added, L's and T's. L stars have an external temperature of 1300 to 2000 degrees Kelvin. Now that is still really, really, really hot, but they have limited nuclear fusion. They are not going to last a long time. They're not going to fuse an awful lot of fuel. They're just not terribly hot stars. Then there are T stars. T stars are known as brown dwarfs. This is an artist's interpretation of a brown dwarf. Brown meaning it just gives off a tiny amount of light, not a big nuclear furnace in there, and a cool external temperature, 1300 to about 700 Kelvin. Now, how are you going to keep the L and the T straight with the others? Well, this is how you do it. Oh, be a fine girl, kiss me later tonight. So later tonight, because then it's the L class and the T class stars, and they are getting dimmer and darker and down to the point that you end up with brown dwarfs. All right, that will do for stellar classification. We'll see you later. Bye-bye.